So we've been talking about Newton's third law and looking at problems related to Newton's third law, and now we're going to start expanding on that. One thing I didn't explain very clearly in class is what we mean by a string. And when we do problems involving strings, we're treating them like they're ideal. And what an ideal string means is that it doesn't stretch, it has no mass, and it has the same tension throughout its length. So these are the properties that make it an ideal string. So you remember in the last handout, we did this problem with 3 carts being pulled by a 6 Newton force. What we have to imagine is that the strings connecting these 3 masses are ideal. So that means they're not objects in their own right. It's not like we have to think the force of the string on the 3rd cart and then the 3rd cart on the string. The string has no mass, so it isn't really an object in its own right. So really it just exists to convey forces between the carts. So 2 on 3, 3 on 2, etc. The same thing is going to be true for this, although we're going to add a new twist, and that is to add a pulley. So questions involving pulleys look like they're 2-dimensional. But with a little trick, we can treat them like a 1-dimensional problem and make them a little bit easier. So we have this problem here, and it has a 20 kilogram mass, which is resting on a surface, and a 5 kilogram mass, which is hanging over the side attached to a pulley. So these two objects are connected by an ideal string, which means it doesn't stretch, it has no mass, and its tension is identical throughout the whole thing. So we want to know what the acceleration of the system is, or the mass of the system of 2 masses. So if the string does not stretch and we let go of the 20 kilogram mass, what will happen to the motion? We're going to start by assuming that the surface that it's resting on is frictionless. You'll probably have to solve something with friction in the homework, but for right now, let's just keep it simple and assume that there's a frictionless surface, so we don't have to deal with friction at all. So then what's going to happen if I let go of that 20 kilogram mass? Well, the 5 kilogram mass is going to be acted on by gravity, and it's going to start to accelerate downwards, right? And since the string doesn't stretch and the tension gets transferred exactly as is, we know that the 20 kilogram mass is going to accelerate at exactly the same rate. And the trick we're going to do for these types of problems is make the direction that the object is accelerating be the positive direction. So normally, you might want to take down to be negative and right to be positive. In this case, we want to make it a consistent direction. So we want to call the direction of acceleration the positive direction. That will help us in our problem solving process. So now, let's see what we have to do. Well, we want to figure all this out. So let's figure out what the forces are acting on each of these objects. So starting with the 5 kilogram mass, we've got the force of gravity, and I'm going to be explicit here. I'm going to say on the 5 kilogram mass. And then we have a tension force, Ft. Well, let's just call it T. T acting up. All right. And then on the 20 kilogram mass, we have another T here. And remember, this spring translates. So what we can say for T, it's the force of the 20 on the 5. And then this T is the force of the 5 on the 20. So these two forces are action-reaction forces. And they are equal in magnitude and opposite in direction. There is no friction on the 20 kilogram block, so there's nothing opposing its motion there, but it's going to have the force of gravity, 20 kilogram, down, and then it's going to also have this normal force up. Once again, I'm going to feel comfortable ignoring the normal force and the force of gravity on the 20 kilogram. You can see that the motion of the 20 kilogram is horizontal only. So the normal force and the force of gravity are going to cancel out. You might be tempted to think that the acceleration of the 5 kilogram is going to be g. Does it equal g, as in 9.8? And the answer is no. And we'll explore the reasons why not. Okay, so let's start by, let's pick an object and start by, so this is something you kind of have to get comfortable doing, just starting the problem. We want to know the acceleration of the object. Let's start with the 5 kilogram mass, okay? So we'll start with the 5 kilogram mass and just set up my force diagram, my net force statement. So F net equals the sum of the forces, which equals ma. Remember, I'm looking at the 5 kilogram free body diagram. So the sum of the forces are going to be, we decided to make down positive, so Fg on the 5 kilogram minus T is going to equal 5A. Are you with me? 5 because of the 5 kilograms, and we don't know A, so I'm leaving it as A. I can expand this Fg and just call it mg, since I know Fg equals mg. So I'm going to say this is equal to 5 times g minus T equals 5 times A. So I have a problem. And my problem is that I have two variables. This is what A is what I'm supposed to solve in the first part, and T is what I'm supposed to solve in part B. Well, I've got two variables and two unknowns, so I can't get anywhere with this. So that means, luckily I have this 20 kilogram mass. So I'm going to go over to the 20 kilogram mass and look at its free body diagram. So writing my FNet statement, FNet equals the sum of the forces, which equals MA. And then what are the sum of the forces in this example? Well, I'm only looking at the horizontal direction now, right? Because I'm interested in the direction it's accelerating. So the sum of the forces for the 20 kilogram mass is just T. And it's positive because that's the direction it's accelerating, sorry. So T is going to equal, now the mass I'm looking at is the 20 kilograms, so it's 20A. So that's it. So these are, again, I'm stuck with T as my unknown and A as my unknown. But the good thing is I've got two equations now with two things that have T and A in them. So it's a small leap to imagine that I'm going to take this equation, sub it in there, and solve. So let's do that. So then we're going to sub and solve. Okay, so then when I do that, I'm going to, let's see, I'm going to have 5g minus, and then T is 20a, so 20a equals 5a. So now let's solve this for a. We can say this is equal to 5g equals 5a plus 20a. So 5g equals 25a. A equals 5 over 25 times g. And so when I solve that out, I get g over 5. Let's see. 9.8 divided by 5 is 1.96. So the acceleration of this object is 1.96 meters per second squared. Now that I have this value, I can solve for t. I can plug it back into t equals 20 times 1.96, and I get times 20, 39.2 newtons as my tension. All right, so this is something that you should feel like comfortable with, actually, and that is not really knowing very much, but setting up two equations with two unknowns and solving from there. Now, there is another way to solve this question. As you know from the previous section, we would chunk these things as one object, right? We would make a system. And in this case, we could make a system of both of the objects. This is my alternate. So you can stop watching, but if you're interested in knowing, we know we have a 5 kilogram and a 20 kilogram. What happens if I put them all together? Well, this is what I mean when I say it's actually not really a two-dimensional problem. It's just a one-dimensional problem. If you put this gray arrow, remember what we were doing? We were putting like a gray box around these two objects. The Fn and the Fg exactly cancel out. So they don't actually come into effect in the vertical direction. But there's no friction, so there's nothing opposing it. So really the only thing you've got acting on this box is the force of gravity of the 5 kilogram block acting on a 25 kilogram object. So when we set up our Fnet statement, Fnet equals the sum of the forces, which equals ma. Let's make this direction be positive because it's going to accelerate in that direction. So setting that up, I get Fg on the 5 kilogram block is equal to my mass, which in this case is 25A. So what is Fg on the 5 kilogram block? It's just 5G, right? 5G equals 25A. A equals 5G over 25. Same thing. A equals 1.96 meters per second squared. So I was able to get the acceleration of the two objects without a system of equations by combining them into one system. Now, this one free body diagram, it does not help me solve for the tension because the tension is internal, right? The tension is in here someplace, and you don't draw tension. You don't draw internal forces on a free body diagram. So we're actually going to need more than just that one free body diagram. But now we can just pick a free body diagram that's easy. For example, we could just say, okay, now that I have that, why don't I just look at the 20 kilogram? Okay, and in that case, the only force acting on it is T. And we already know the acceleration is 1.96 meters per second squared. So now when I set my Fnet statement equals ma, I get T equals mass, which is 20, times A, 1.96. So my T works out to the same thing, which is 39.2 newtons is the units. So those are my two answers. So I got those doing it a slightly different way. Either way works, and they're perfectly acceptable. It's just sometimes you have to do one way, sometimes you can do either way. It really just depends.